Hello everyone, my name is Huaiyu Zang, a biostatistician working at the Heart Institute Department at Cincinnati Children's Hospital. It is really an honor to be able to present my research work titled A Bayesian nonparametric Approach for Causal Inference with Missing Covariates. This work is joined with Dr. Han Kim at the University of Cincinnati and Dr. Bin Huang at the Cincinnati Children's Hospital. This research work is motivated by a juvenile idiopathic arthritis study. The goal of this study is to estimate the effect of different treatment options. This JA data shares some unique features, such as it has a large number of mixed continuous and categorical covariates with complex data distribution and a missing baseline measure. To analyze this data properly, we propose Bayesian nonparametric causal models. Our model simultaneously imputes missing covariates and estimates average treatment effect. Thus, it can propagate the uncertainty of missing covariates to the final causal inference. In addition, our model can capture complex data distribution and allow for the mixed type of covariates in the imputation. Now let me start with some introduction of causal inference. As we know, observation studies are designed to find causal effect. Like randomized trial, the researcher does not control treatment assignment. One challenge to analyze observational data is the confounding problem. In this figure, X is the pretreatment covariates, like age. A is a treatment indicator, and Y is the outcome, like disease. We can see that X affects both A and Y. As a real-life example, if older people are at a high risk of disease and more likely to receive treatment, then age is a confounder in this case. To reduce confounding problem, a widely used method for causal inference is propensity score-based method. The propensity score is defined as the probability of receiving a treatment given covariates. In frequentist paradigm, propensity score are used in matching or weighting. Both matching and weighting method are motivated by consistency and asymptotic normality in the frequentist inference. It requires large sample size. In addition, causal estimation may suffer if the propensity score is misspecified. When we have a missing covariates, many causal methods cannot handle it directly. In practice, they either discard the missing value or impute the missing value first, followed by applying in the causal method to the imputed data. One exception is Ray and others, 2018. They propose a BNP approach to causal inference with missing covariates, utilizing an enriched Dirichlet process prior. Their approach performs well in which the outcome is binary and data has a missing covariates. However, it is not clear if their approach can handle the missing covariates problem when the data has a continuous outcome. Now let us talk about the detail of our proposed model with the prior distribution construction. First, we describe our model notation. D denote the categorical covariates and transform to D star of size PD star in the modeling. CI denote the continuous variable. The first element represents the outcome variable Y, and all the others represent continuous covariates of X. T is the treatment vector. The first element is treatment indicator A, and all the other elements are just vector of 0. R and S label the mixture component for C and D respectively. And for continuous model, a continuous variable given the covariates, categorical covariates D and treatment vector T, we use a truncated version of DP mixture regression model. Here, delta is the regression coefficient of the treatment indicator A. It has a desired average treatment effect interpretation under standard causal assumption. Delta measures the difference in the mean level of outcome variable y, where variation due to the level of categorical covariates are already explained by the BD part, and dependence between outcome variable and continued covariates are explained by the covariance function. And for the categorical variable D, we use a DP mixture of product multinomial distribution. Note that the vector T is not included in the categorical component modeling. It is only introduced to be conditional on C in the continuous modeling component modeling. And we require that the missing at random assumption, which means the missingness only depends on the observed variables. This assumption implies that the missingness mechanism can be ignored in the modeling. For the prior on the components' weights, we assign a hierarchical prior and introduce a third component K that incorporates new forms of local dependence. For the probability vector of mixture component index, we assign a truncated stick breaking process. For the prior of the data model parameters, we use a conjugate prior to simplify the computations. Here is the graph representation of our proposed model. We can see the association among and between different variables. We see that the association among the categorical variable D can be captured by S. The association among continuous variable can be captured by R. And the dependence between C and D can be captured in two ways. One way is through component-specific regression function and covariance matrices. Another way is captured via the hierarchical structure of mixture components. Given our proposed model, the response surface of outcome can represent a flexible function form. And when we have a missing covariance in D or C, imputation becomes straightforward. We simply sample from the full conditional distribution for the missing values within the GIP sampler. Now we describe simulation studies. Four existing causal models are presented as our method competitors. First one is BART. Second one is linear model, adjusting for all confounders. Third is IPTW, and fourth is TMLE. When we have missing data, three approaches are compared. First one is complete case analysis with existing causal models. Second, we apply the existing causal model to the imputed data, where we impute the missing covariates by the multiple imputation by trained equation mice. For our model, we set the upper bound of occupied component K equal 20, R equal 30, and S equal to 50. The ATE estimate is obtained by averaging over 2000 MC iteration from the GIP sampler after discarding the first 2000 iteration as burn-ins. We conducted two simulations. First simulation has a continuous bimodal outcomes, and it mimics the scenario 3 in Wright and others 2018 papers. The second simulation aims to understand behavior of model in data whose shape is complicated. And both simulation, we perform a repeat sampling study and generated 200 data set, each with sample size n equal 500. And our simulation results show that our model produce an ATE point estimate with the lowest RMSE and MAE, and the coverage rate is close to the nominal coverage, 95%. Our model also had a good imputation performance. In preserving the joint distribution under both simulations. Due to the pre-recording time constraint, I cannot go over the detail of the simulation result. I will discuss more about simulation results on the online meeting if possible. Now let's move on to our case studies. The JI case study has two treatment comparison options, earlier aggressive approach versus a conservative approach. Our outcome is the clinical juvenile arthritis disease activity score at 6 months, CJDAS at 6 months. 5 continuous covariates and 8 categorical covariates are considered as confounding factors based on our subject matter knowledge. Most covariates have a missing value. For some, the missingness is substantial. So if we deleted the missing covariate and run the complete cases-only analysis, we end up no data at all. For our proposed model, the AT estimate was obtained by averaging over 30,000 posterior MC jaw after 5,000 burn-ins. For comparison purpose, we apply the existing causal model to multiply imputed data set generated from mice R package with the predictive mean matching method. Here is our results, and here is the trace plot histogram of causal effect drawn from our proposed method. We see that the posterior mean of estimated causal effect from our model is minus 1.73, which is interpreted as the earlier aggressive plan is more effective than the conservative plan by decreasing the disease activity on average by 1.73 points. And the 95 credible interval also did not comprise a zero value. The posterior probability of that the treatment is less than zero is around 99%, which also suggests that the earlier aggressive approach is more effective than conservative approach. For the existing causal model applied to the imputed data set, mice plus LM only shows a significant negative causal estimate, while others only estimated non-significant negative causal effects. To conclude, I would like to emphasize strengths of our proposed model. First, our model is flexible and data adaptive. Second, it propagates the uncertainty of missing covariate to the final causal inference. Third, it can allow the mixed type of covariates in the imputation. Fourth, it produces multiply imputed data for the future research use. Finally, it can present a good summary for communicating results and provide comprehensive distributional information rather than just provide a point estimate. That's what I have today. Thank you. I listed all the reference in the slides here. And here is my email address. Shoot me an email if there are any questions. Thank you.